Okay, so here's the calculation for the period, and how long it takes the sun to go around the galaxy. So the period, just the distance travelled, circumference of the orbit divided by the speed. So r is 8 kiloparsecs, so you can see 8 kiloparsecs here, and then here's the 220 kilometers per second. Make sure you put everything in SI units. Answer comes out in seconds, and if you work that out, then it's about 250 million years. Okay, so that's how long it takes the sun to go around the galaxy once. So the sun is much older than that. The sun is about 5 billion years. Okay, so that means that the sun has been around the galaxy about 20 times already in its lifetime. And so, in the context of the wind-up problem, then clearly the constituent components of spiral galaxies have made many rotations, which would make the wind-up problem very bad if it was true that the spiral pattern was fixed in the stars themselves and the gas. So that can't be true. So therefore we need a different theory, and that theory is referred to as density wave theory. Okay. So it's still a subject of research really as to how spiral galaxies exactly work, but this is the current thinking. So the spiral pattern that we see in spiral galaxies, you should think of it as a wave pattern. Okay, so a little bit like water waves in a sense. You can get a wave moving through a medium, which is sort of independent as to how the medium itself is moving, and so you can set up a wave pattern. And in the context of spiral galaxies, this wave pattern is actually rotating around at a slower speed than the components of the galaxy itself. Okay. So this is a little bit counterintuitive. Okay. But let me try and explain what we mean. Okay. So as I mentioned, we've already ascertained that stars and gas can't be fixed in the spiral pattern, so therefore stars and gas move in and out of arms over time. So as a star like the sun is rotating around the galaxy, it's going to go in and out of spiral arms as it encounters them. But the spiral arms pattern is moving slower than we are. Okay, so that means that we enter the spiral arm in effect from what appears to be the sort of back of the spiral arm and come out the front side as if you're looking at it. We'll have a look at a diagram in a moment. A key thing here now is that the spiral arms act to collect material together. Okay, so the spiral arm is a slight deepening of the gravitational potential well, and when stars and gas enter into the arm, they get slowed down a little bit. So effectively, it's a little bit like a pile-up or a traffic jam. Okay, and again, I'm sure if you've ever travelled on a motorway where it's quite congested, there's a lot of traffic, you can get waves of stop-start rippling down the motorway, even though the cars are all traveling at 70 miles an hour. They can slow down, and then you get a concentration of cars for a while, and then for no apparent reason, everyone takes off again and it gets going. If you look at that from above, it's like a wave pattern that's traveling back down the motorway. So that's a very good analogy for how spiral arms are working. So as clouds of gas, like the H1 clouds, the atomic hydrogen clouds, as they enter a spiral arm, they will get compressed because they're all sort of piling up into the back of each other. That makes them denser. They've got a lot of dust in them, which excludes the radiation, which allows molecules to form. Everything cools down. That allows gravity to get to work, and then the cloud can collapse and start to form new stars. So this is why the spiral arms are marked out as the regions where new stars form in spiral galaxies. Okay. And so that allows them especially to form the massive stars. And so all of the massive star phenomena are associated with spiral arms. Just another little note that basically spiral arms sort of trail the rotation. So the way that the sort of pattern of the spiral arm goes is how you would expect it to go from the direction of rotation. Okay, so let's have a look at this picture, and we will hopefully explain all of that. So the first question to ask yourself is, which way round is this galaxy rotating? Clockwise or anti-clockwise? So the fact that the spiral arms are trailing the rotation means that this galaxy is rotating anti-clockwise. It's going around this way. Okay. So if we take stars and gas on an orbit here, say, okay, so if you can see my cursor, so they will be, stars and gas will be rotating around this way, and they are rotating faster than the spiral arm pattern. So they will catch up this spiral arm, and material will enter the spiral arm from this side. Okay. So again, that's what I mean by counterintuitive. You tend to think of the spiral pattern going around like this, and that material would enter this side and come out this side, but it's the other way around. Okay, the spiral pattern is coming back towards us because the actual individual stars and clouds of gas are rotating faster than the spiral pattern itself. So this spiral pattern comes back towards us here, and we enter in this side. And you can see on this side where the gas and dust are entering the spiral arm, that is where you see the dark dust lanes here. Okay. So that's where all the molecular cloud and dusty material are being collected up and piled up. So you get the dust lanes on this side of the arm. Okay. And then a bit further along, you can see these red patches, okay, like here and here and here. So those are the H2 regions, okay, so those are the H alpha light shining very brightly in this object, okay. And then sort of here, just past it, you can see where all the blue light is coming from, and even sort of clusters of blue stars here, okay. So that blue light is all the population 1 stars. These are all the massive young hot stars, okay. So that really delineates the spiral arm. That's the population 1 stars that are showing blue. You can see them all here on this arm as well. Okay, so there's an age differential across the arm here. So you've got raw material for star formation getting collected up and compressed on the way in. The signs of star formation in terms of H2 regions here, and then you've got the young hot clusters of stars, just like the open clusters that we talked about earlier in the course. They all inhabit this spiral arm. Okay. But then if you think a little bit more about this, we just did the calculation for the sun. It takes 240 million years to go all the way around the galaxy. So it only takes a few million years to go across the arm and out the other side. But the most massive stars, their main sequence lifetime is only a few million years. Okay. So the massive stars basically live and die within the spiral arm itself. So the supernovae will all be going off in these spiral arms. The type 2 supernovae, okay, from the exploding massive stars will be going off in the spiral arms here. Okay. So that's the idea. Okay. So all the population 1 type activity and phenomena, star formation and stellar death from the supernovae are all going on in these spiral arms. Low mass stars, like the sun, you know, the sun would have formed in this, probably in a very similar way in one of these clusters, but then it will have, you know, it lives for 5-10 billion years, right? So it'll carry on out the other side, and over time it'll go in and out of the arms many times as it goes around the galaxy. Okay, so yeah, I think that's it all right. Okay, so in workshop 4, I think, yeah. We didn't get to it in the workshop, but it's there on the workshop 4 website. I've given you multi-wavelength pictures of a spiral galaxy, very like this one, a face-on view. So what I want you to do there is to go through that with all of this in mind, the idea that what are the components of a spiral arm, and what wavebands are they emitting strongly in, okay, like hot stars, like the dust, like H2 regions, and like molecular clouds, okay. So which wavebands are picking those out, and do they indeed just pick out the spiral arms? And then for other wavebands, which ones trace the sort of old star population, the population of cool stars, okay. So that's very much what you should be doing now. With you've been armed yourself with a lot of multi-wavelength information about what different wavebands are probing, and put yourself to the test with all those multi-wavelength pictures, and see if you can piece together a picture for yourself, okay, and make sense of it. Okay, so the last component of the galaxy we want to look at is what's called the halo. So that's now not talking about the plane and the disk of our galaxy at all, where the spiral arms are. There are components of our galaxy that inhabit all around a much larger spheroidal sort of volume around our galaxy. They're still very much part of our galaxy though. And so it's a spherical halo of objects, okay? The most conspicuous objects up there in the halo, so above and below the disk, are the globular clusters that we met back along. There are also individual stars. They probably were in globular clusters at some point, but probably got ripped out. So these are referred to as halo stars. Okay. But there are not very many of those. So the globular clusters are the main component of what we call the galactic halo. And it is much bigger than the disk itself. Okay, so the disk is a radius of, like I said, 20 kiloparsecs. The galactic halo, so the globular cluster, extend way past that, out to around about 100 kiloparsecs. Okay, so that's the full extent of our galaxy. And so these globular clusters will still be, gravitationally bound. They are part of the galaxy, so they orbit around the center of the galaxy as well. But they don't orbit in any organized way. They're not all going around in the same direction. They just do their own thing. So just to remind you what a globular cluster looks like. Okay, so that's what we're talking about again with globular clusters. So those tightly bound clusters of 10 to the 5 stars or so, and these are all very old. Remember, so they're the low metallicity old population 2 stars. So here is a couple of diagrams to show you the distribution of globular clusters in the galaxy. So first of all, sort of the ones that are fairly close. There is a concentration of them sort of towards the bulge of our galaxy, and you could think of the bulge with its sort of spherical shape as also being a similar related population to the halo. In fact, okay, it's a spherical thing and not a disk thing. So this XY view here is the view from our sun looking in towards the galactic center in here. So the plane shown schematically here. And each dot here represents a globular cluster. So that's the view of the globular clusters from the sun. This is a sort of side-on view. So here is here's the sun now. So this is a cross-section through the galaxy, showing you where all the known globular clusters are. Now, there seems to be a dearth of globular clusters over here. But of course, these searches are done in the optical. And I'm sure from the pictures earlier in this lecture, you can understand why we don't know about very many globular clusters over here, okay, behind the rest of the Milky Way. You can work that one out for yourself. They will be there. It's just that we have trouble seeing them. Okay, so there's quite a lot of globular clusters in and around the bulge, but then this is the real halo population up here, and it extends much further than that. Okay, so this is now a sort of a zoom out, if you like. So here's the Milky Way galaxy just in the middle there now. Now we're up at scales of 100 kiloparsecs, or even 200. Well, yeah, 200 above and below the plane of our galaxy, and we can see that there are globular clusters all the way out here. Okay. So really, our galaxy is a much larger entity than just the visible disk that we can see. So the globular clusters extend way past that. Okay. And in a sense, this is linked up with issues to do with the rotation curve that I talked about before, and we will come to in workshop 5. But really, this is all to do with the fact that it's really dark matter that is holding all of this and determining the dynamics of it together. Of course, is something we can't see and we don't understand, but we'll come to that in workshop 5. So just to summarize visually what we've learned in this lecture then. So these are the components of our own Milky Way. Okay, so you should be familiarize yourself with this kind of diagram. Okay, so we live in a barred spiral. Here's the disk of our galaxy. Here's the bulge, and there's a bar in there. We live about 8 kiloparsecs from the center, and it will extend out to sort of 20 or 25 kiloparsecs in terms of the disk. But then you've got the halo that extends all the way around it, populated by the globular clusters. So just to sort of piece that together a little bit and talk about, just to try and set some context here. So you can see that there seem to be sort of almost 2 competing facets of our galaxy. So we've got this spherical halo and the bulge as well, it's being spherical. And the idea is that that spherical part of spiral galaxies, and not just ours, actually forms first. So when galaxies like our own first formed, they will have formed out of sort of metal pore material that, emerging from the Big Bang itself. So mostly hydrogen and helium, very little heavy elements, because there've not been hardly any generations of previous stellar evolution. So that metal pore material, just a great big spherical clump, collapses, fragments, and forms all of the spherical halo components, so the globular clusters, basically, probably the first things in our galaxy to form. You yourself, found that when you found out the ages of them. They were all, approaching sort of 10 billion years old, so very, very old. So basically that's kind of how old our galaxy is, if you like. And they had one great big burst of formation, and then, nothing ever formed again after that. Okay, up there in the halo. There's no gas, no dust in the halo, no staff motion going on at all up there. You've just got these aging populations. A little bit like mini elliptical galaxies. So the idea is that the disk of the galaxy came along later. So material kind of getting pulled in, but this time with significant angular momentum, so that it sets up a disk rotation pattern. Okay, and then in that disk rotation pattern, the spiral arm sort of pattern gets going, and it kind of turns into a sort of continuous star-forming machine, really, the spiral arms in a galaxy. You get lots and lots of cycling of gas and dust into stars, and then the stars evolving and going supernova and planetary nebulae, etc., enriching the interstellar medium in heavy elements, and continually cycling, and that's been going on. So basically, star formation in the disk is thought to have been going on continually, for several billion years, well, many billion years. And so that's why we now have the metal-rich population 1 objects in the disk of our galaxy. Okay. So the bulge, is a little bit different again. So it's got some metal-rich stars, as well as the metal pore stars. So again, probably something to do with the initial spherical halo population. But it's also thought to be where a lot of stars end up when other little galaxies merge in with ours. So like the Magellanic Clouds that are orbiting us at the moment, eventually those galaxies will be gobbled up by the Milky Way itself, and they're slowly spiraling in and getting captured. I showed you that picture on the near-infrared one earlier of a galaxy being sort of stretched and morphed by its gravitational interaction with our much bigger Milky Way. So again, all of those stars will end up in the Milky Way somewhere, and a lot of them will find their way into the center, where you get this bulge population. So that's the idea of how the galaxy was put together, but that's still very much a subject for research as to how galaxies form and evolve over time. So let's summarize all of this. So our galaxy is a barred spiral, subclass B or C. We've got a disk with spiral arms in it, surrounded by this spherical galactic halo that we just talked about. So the halo is made up of population 2 objects and was formed first, and then the disk with population 1 objects has come along later. Okay, so as well as the testing your multi-wavelength skills on the pictures of the M101 spiral galaxy in the workshop 4 exercise, then here I'm going to direct you at another little multi-wavelength exercise, but this time looking at multi-wavelength images of our own Milky Way. Okay, so I'll just flash that up for you. Okay, I'll come back to it in a moment. So there are, over half a dozen or so different wave bands there. We've covered all of them in the module so far. Okay, so you should have the physical background to understand what you're looking at in each wave band. Okay, so think about, again, what component is dominating the emission in each wave band. Ask yourself, are you looking at stars or gas or dust? Those are the 3 components. Okay, how is it emitting? Is it a spectral line or is it a continuum? If it's continuum radiation, do you think you can apply sort of Wien's displacement law and then think about the typical temperature of objects that will be emitting at those wave bands and dominating the flux? And then ask yourself why they all look different, right? So why do they look? Why is the emission distributed as it is? And once you start to decode that, you can look for sort of correlations and anti-correlations between the different patterns in the different wave bands. Okay, so if there are certain things that will pick out sort of massive star-forming regions, for instance, then do they all look the same, even though they're probed at different wave bands? Okay, so here is the pictures. Okay, so they go all the way from you've got long wavelength radio continuum. Some of these are in frequencies, apologies. You can convert those to wavelengths, but this is basically meter wavelength. This is more centimeter wavelength radio continuum. Here's your atomic hydrogen, which is 21 centimeter line emission that we talked about. Molecular hydrogen, but this is actually a map of carbon monoxide, but it traces molecular hydrogen. And then you've got 3 different infrared bands. You've got the optical, so we saw these 2 in the lecture already. And there's an X-ray one here as well. Okay. So, so have a look at the patterns that you can see here. They look, some of them look similar, some of them look different. Why do the ones who look similar, and why do the ones that look different? Okay. So you've got some anti-correlations, like the dark dust lanes here look similar to the patterns in the molecular hydrogen here. Ask yourself why. Okay, and try and answer why. Okay. So that's a little exercise for you. I think you might be able to spot a sort of a supernova remnant on here as well, maybe even 1 or 2. Yeah. So again, think about all of those. It's a nice way to bring together and revise everything you've learned in a sort of multi-wavelength facet so far in the module. And it is a key component of the module. Okay. So these skills you can take forward into later modules. Have a go yourself first. The website is here. There are some explanations there. There's a link on on the Minerva web resources to all of this as well that you can go and check up on afterwards. So I won't go through it because you can go here and read all about the answers as well. But I would urge you to have a go yourself first. Okay. I'll leave it there for now, and in the next lecture we will start to look a little bit what I was just talking about galaxies that collide and merge, and then do even more crazy things with the supermassive black holes in the center. Stop recording.